This video is the solution for question 8 on page 501 of text and test 4. So in this question we want to prove that x plus x squared plus x cubed plus up as far as x to the n equals x times x to the n minus 1 over x minus 1, and they make the obvious statement here in the question that x can't be equal to 1. And that's just to prevent there being a division by 0 on the right hand side here. So first of all, let's do our p1. So we're going to take this proposition and see if it's true for 1. So that means I just use the first term on the left hand side, and it's obviously going to be x to the power of 1. Just watch out here that the n is what we're replacing, and of course the n in that case is going to give you x to the power of 1. Okay, so on the right hand side then, it might be a bit more obvious if I put brackets around that x minus 1 at the bottom. You can see there's a common factor of x minus 1 in the numerator and denominator, so that can cancel out, leaving you with x equals x. And of course that's quite clearly a true statement. Let's move on to pk. And so this is simply a rewrite of the original statement with k's instead of n's, and we're making the assumption that this is true. So we'll say pk, assume it's true. And we go then to pk plus 1. So this is just going to be the previous statement with one extra term. Again, like I've said to you before in class, just make sure that it's really clear this minus 1 is not part of the exponent at this stage. So now I'm going to look at my pk plus 1 and I'm going to use replacement from the pk line. And here's the information underlined that comes from that pk statement. So I'm going to be able to replace this portion of pk plus 1 with the right hand side of pk. So at this stage, this is my equation. So I can see quite clearly that I've got fractions across this equation. So I'd really like to eliminate that if possible, and I can do that by multiplying the whole equation across by x minus 1. So let's think about the effect that's going to have. Well, for this first term, it's just going to have the effect of crossing out this denominator here. For this term here, it's going to result in multiplication by x minus 1. We'll have to write x minus 1 in front of that in brackets. And for this last term here, then, we're going to end up being able to cancel out the x minus 1. So that leaves me now with this line, and I'm going to just have to do a little bit of algebraic work here to resolve it so that both sides are equal. Probably the easiest thing to do here is just multiply out straightforwardly. So having a look at that, and just taking care with each term, x by x to the power of k. Well, remember this is an x to the power of 1. So when I multiply, I add my powers. So that's going to be an x to the power of k plus 1. And then I've got x multiplied by minus 1. So of course that'll just give me a minus x. And again now I'm going to multiply x minus 1 by x to the k plus 1. So x by x to the k plus 1, well, this x is an x to the power of 1. So multiplication means that I'm going to have to add my powers. And that's going to give me x to the power of k plus 2. And then again, minus 1 will multiply by the x to the k plus 1, giving minus 1 times x to the k plus 1. Or you could just write this as minus x to the k plus 1 if you liked as well. On to the right hand side, again, this x is an x to the power of 1. Multiplying it by x to the k plus 1 will give x to the k plus 2, and then finally x to the 1 minus times minus 1 will give me minus x or minus 1x. So just a little bit more tidying up then. I can see on the left hand side I've got x to the k plus 1 minus x to the k plus 1, so these two are going to cancel off. And then I'm going to have on the left hand side x to the k plus 2 minus x, and on the right hand side x to the k plus 2, and on that side also I've got a minus x. So since both sides of the equation are the same, clearly this is true. And now I want to just put in my little spiel at the end to finish up my induction. So I can say that the statement is true for n equals 1, and since it's also true for n equals k plus 1, that leads on then to for us to be able to say that it's true for n equals 2, 3, and all values of n where n is an element of n.